Good morning, and welcome back to the FAA production studios for Sun and Fun 2008. I'm Cheryl Hardy, and we're glad you're with us this morning. We're getting ready to resume our regular programming schedule, and we'll go right to Walt in Studio A.
Our next presenter is a corporate pilot from Chicago, Illinois. He's a 5,000-hour ATP pilot. He has type ratings in the Learjet and the Citation business jets. He's a Gold Seal flight instructor for airplanes, instruments, and multi-engine. Eric's background includes flight instruction, charter, corporate flying. He spent 2 years as a TV weatherman in Southern Illinois and is currently working on a master's degree in aviation. Eric is a well-respected aviation safety speaker throughout the United States, including working with EAA in Oshkosh and with Sun and Fun. We're very pleased to have him back, and I'm happy to introduce our next presenter, who's going to be talking about surviving forced landings. Let's welcome Eric Basile.
Thank you, Walt. Welcome to another beautiful day at Sun and Fun. Happy to be here. My name is Eric Basile, and my topic is surviving forced landings. You know, forced landing is probably really high up there. It's probably number one or number two emergency that pilots fear the most, probably other than a fire in flight. And so the purpose of this presentation is to discuss some issues that you may not have thought about lately and put an emphasis on the concept of surviving a forced landing. We want to turn it into something that is a manageable emergency situation and teach you some tips and tricks that will allow you to manage that dreaded emergency a lot easier. Now, there's a number of keys to successfully executing a forced landing, and it really starts with proper pre-flight planning. That's even before you get in the air, even before we start talking about mechanical problems with your airplane. Proper pre-flight planning is very important to understand, to making an outcome a lot better. Also, we're going to discuss the importance of understanding airspeed. And there's not just one airspeed that you need to understand with emergency landing, so we're going to get into that a little bit more. We're also going to talk about how to cope with stress. Every emergency situation involves a great deal of stress, and we're going to talk about some techniques to deal with stress. We're also going to talk about the importance of knowing your airplane and knowing how to fly it precisely to be the master of your airplane in an emergency situation. Finally, as we get down to the completion of the emergency landing, we're going to talk about approach and impact management and how to survive these situations a lot better. And lastly, we're going to emphasize the importance of practice. So I start out by posing a little bit of a rhetorical question, and this is a little bit of an old incident, but you could go through the database and find any number of accidents that have occurred more recently just like this. This was in central Illinois in 2001. So a gentleman was flying a Piper Cherokee 6. He took off from a private strip and he was headed up to Oshkosh. So when I first started making this presentation, this was a current accident. Gentleman lost power on takeoff and he stalled while he was in a turn, and unfortunately there were 2 fatalities. Now, the probable cause that the NTSB determined, and it's quite lengthy, basically it had to do with the fact that he stalled the airplane, but there was fuel starvation, and it was due to an incorrect fuel tank selector position. And rather than continue to land straight ahead, he decided to make a 180-degree turn back to his point of takeoff and stalled during the turn. Most importantly, however, observation of the surrounding farmland revealed that there were plenty of suitable areas to execute a forced landing. So what is a forced landing? Well, the FAA defines this as an immediate landing on or off an airport necessitated by the inability to continue flight. So for whatever reason, the aircraft engine has failed and you have to execute a landing. We're going to talk a little bit about engine failure causes, and you'll see that this is statistics for the calendar year of 2000. Well, why did we pick the year 2000? Well, there's a number of reasons. First of all, year 2000 was a year where the economy was good. There was a great deal of general aviation activity. So the statistics from 2000 represent what we would consider to be an average year of general aviation activity. Secondly, it's far enough in the past that all of the accidents have been thoroughly investigated and probable causes have been determined. So looking at the data from 2000, we see that the bulk of these accidents were related to what we call fuel mismanagement. And fuel mismanagement accounts for three different things. We have fuel contamination, fuel starvation, and fuel exhaustion. And there's a difference between those. Fuel contamination is fairly obvious. Fuel starvation is where the aircraft had fuel on board, but for whatever reason it was not getting to the engine. Either the fuel selector was set to the wrong tank or there was some sort of mechanical difficulty. Whereas fuel exhaustion means there is absolutely no fuel left on board the aircraft. And so you can see that represents the very large portion of these accidents. We also have carburetor icing, which represents a small segment, and then we have about 10%, which is what we call improper maintenance. And what that means is either the overhaul on the engine was not done properly, or unapproved parts reused, or something like that, or was not approved maintenance and caused a mechanical problem there. So what's the upshot of this graphic? Well, what I want to point out to you is when you say, oh, I had an engine failure, people's minds automatically go to, cylinder blew up or a connecting rod failed or something like that. And you can see that pure mechanical failures represent only about a quarter of all the engine failures in this time period. So just a pure mechanical failure is not as common as you might think. Instead, almost, or actually more than half of the accidents represent causes that are in one way or another directly controllable by the pilot. And the pilot has an incredible amount of control over the fuel, how much fuel you have on board, knowing how much fuel you have on board, making sure it's the correct grade and it's not contaminated, making sure that your fuel selecting equipment is in proper working order, and making sure that you do your engine work and your overhauls at reputable facilities and that everything is signed off properly with good parts. And so if you do all those things, you eliminate 50% of your risk of having an engine failure right there. So that's kind of my first point, is that it's not just an emergency that happens and it's really sort of out of your control and you just have to throw up your hands and give up. Really, you as the pilot have an incredible amount of control over your risk of having an engine failure. And even if you do have an engine failure, there is absolutely no reason at all for just having an engine failure to result in a serious or fatal accident. You are the pilot in command of your airplane, and an emergency situation, while stressful, is something that you can manage as the pilot. You are the master of your airplane, even in an emergency. And so if you understand the keys to preparing for an emergency and understanding the techniques that you need to use, it will allow you to have a much more enjoyable outcome. And part of preparing for this starts well before the flight. So the first talk about pre-flight preparation is the importance of knowing your terrain. Looking at the left side of this graphic, how would you treat flying through this terrain as opposed to flying through this terrain? This is out in western Colorado here, and this is in central Illinois. You can just see by the colors on the sectional that there's a lot more terrain here. There's a lot fewer suitable places for emergency landings, and so consequently, if you're flying in this area, you really have to take the time to do good pre-flight preparation and think about, well, what am I going to do if I have an engine failure? And you're going to plan your flight in such a way that it allows for more options. You're either going to fly at a higher altitude, or you're going to adjust your route of flight, maybe follow this interstate highway here because it's probably following valleys, and look at the elevations along the way, look at suitable areas, and you might adjust your route of flight so that you bear more towards airports so that you have more options available in case you start encountering engine problems. So the first thing is the importance of knowing your terrain and not being GPS dependent. Now, how many people here in the audience fly an airplane that has a GPS of one sort or another in it? Pretty much almost everybody, and this has been the case for quite a few years now. But let's be honest, pretty much everybody gets in their airplane and hits direct to wherever they want to fly to, and they follow that great, beautiful magenta line right to their destination. And I'm not saying that you have to go back to the days where you're drawing a pencil line on a sectional and following your course within a mile or two. GPSs are great. But the thing is your focus becomes so much on the GPS that people naturally start to tune out a little bit what they're flying over, because you're flying a screen rather than looking outside the airplane, and you may not really care where you're flying at within a few miles. So you have to try to force yourself to keep your attention outside the airplane and understand what's available to you outside the airplane in case you had an emergency. I tell a story, this is apocryphal, but it's still a lot of fun. A guy took off from somewhere in Montana, like Bozeman, Montana or something like that, and he called up Salt Lake City Center. He was in a 172 and he was looking for VFR advisories. So he calls up Salt Lake Center, this is Skyhawk 1, 2, 3, 4, 5, looking for VFR advisories. And the controller says, well, say your position and altitude. He says, well, I'm 863 miles northwest of Lincoln, Nebraska. And the controller said, well, do you have anything closer? So that just gives you an idea of, the GPS is so transfixing, you're looking at your distance and your time to your destination counting down. And so you might just get dependent on following that rather than understanding what's below you. And so consequently, you start to lose situational awareness a little bit. So some techniques to improve your situational awareness and your understanding of what you're flying in would be, first, you might carry an expired sectional with you in the aircraft, always I'd recommend a current sectional, but even an expired sectional will still show you where terrain is. And you could just use that to follow along your route of flight. Another option for those of you that are EAA members in the audience is you can use a website called aeroplanner.com to study the route beforehand. I like aeroplanner.com because EAA members have free access. You can punch in your route of flight. You can use whatever navigational technique you want, and it will display your route of flight for you in little convenient kneeboard-sized sectional pieces. So like a 3x5 or 4x5 piece of sectional, you can print that out on your computer, and then it's got your course line drawn through it, and you can just flip through as you go along. And so you see probably 30 miles either side of your course line what's around you. So you could divert to an airport if you had an emergency or ran into trouble. And so it's a lot more convenient to use that than flipping through an enormous sectional. Secondly, and this is another big point, is study the local airport area on arrival. Because generally when people are flying into an airport, okay, you've finished your trip, you're just about to land at your destination, where are your thoughts right now? Your thoughts are on landing and what you're going to do once you arrive at the destination, right? Your mind has already moved forward to what the plans that you have or whatever activities you have when you land. And so you may not be necessarily paying attention to the area around the airport, especially if it's an unfamiliar airport. But then think about it. You're going to land, right? Well, of course you're going to have to take off again. And if it's an unfamiliar airport and you lose your engine shortly after you take off, wouldn't it be a nice thing to know that you'd looked at it beforehand? You say, oh, there's a nice big open field just ahead and to the left of the departure end of the runway, rather than get in the air a couple hundred feet up and then have engine problems and not really have any idea where you're going. So take the time to study the local airport area on arrival. Another good option that's come up recently is to use Google Earth. You could use Google Earth or some sort of satellite map program on the internet to look at any airport you want, and you can study the whole area around the airport, see what kind of open areas there are, what kind of obstructions there are. Next, plan your routes as best as possible to provide suitable landing areas. So, if, like we were talking about, if you're flying through the mountains, don't just fly GPS direct from A to B because it's convenient. You might alter your course just a little bit. That would allow you to fly over more airports, so you'd have more opportunities for diversion. If you started having mechanical problems, let's say your engine starts losing power, but it hasn't really completely lost power, you might be closer to a suitable airport with maintenance and other kind of facilities. And lastly, of course, consider increasing your altitude to provide more time and more options and a better gliding distance if you have an emergency. So, okay, so we've done the pre-flight planning and we've looked at the terrain and we've planned our flight out. Now we're in the air and we start having mechanical problems. Now the first thing I want to say is, how many of you think that most engine failures are where the engine dies completely? I mean, it's a good portion of engine failures, but there's just an equal portion where the engine loses a partial amount of power, but some power is still available. For instance, let's say you had a stuck valve. Well, the whole engine's not going to quit. Of course, it's going to vibrate and it's going to put out some reduced amount of power, but that will probably be enough to get you to an airport. And so consider that, first of all, if your engine starts to lose power, the first thing you're going to start to do is think about where you're going to head to, and hopefully if you've done pre-flight planning, you know that there's a nearby airport. Head in that direction, and then consider adjusting your airspeed in case you do lose the engine completely. Then you're at the proper airspeed to glide to an appropriate landing field. So let's talk about speed. This is a very important concept here. Everyone here in this room has heard of best glide speed. It's a very familiar concept taught from the very beginning of flying. And so what does best glide speed give us? Well, by definition, it gets us the greatest forward distance of travel per unit of altitude that you lose. It is equivalent to the L over D max speed for your airplane, or maximum range speed. So that's great to know that this is the speed at which, if you need to glide far to a specific point, that would be the proper speed to fly at. But the problem is that is all that people think about. And so people kind of have this rote understanding that if I lose my engine, the speed I'm going to fly at is best glide speed. And typically they burn whatever number is in the POH into their head. We're going to talk about a lot of things why this is a bad idea to just memorize one speed. But first of all, finishing up our discussion of best glide speed, the first problem with best glide speed is typically the best glide speed is only published for maximum gross weight. Well, what's the problem with that? How often do you fly at maximum gross weight? You're only at maximum gross weight once, and that would be at takeoff, even if you loaded the plane to the gills. You could only be at maximum gross weight at one instant. And as soon as you lift off, you're starting to lose weight through burning fuel. And then of course, if you have less fuel or less passengers, certainly you're below maximum gross weight. The problem is that speed is only published for, at one speed at maximum gross weight. But like any performance speed, it's a dynamic speed. It varies with weight. And so, I'm backing up now here. There we go. So, you can approximate best glide speed for a lower weight. Well, how do you do that? Well, I'll show you. There's a formula, and I want to preface this by saying I am not a mathematical genius by any means. Math and I do not get along. So this is the most complicated math you will ever see coming from me. But basically the way to compute best glide speed for whatever condition you're at, you're going to take the published glide speed for maximum gross weight, and then you're going to take whatever weight you're currently at in your airplane, divide that by whatever the maximum gross weight is, take the square root, and then multiply the two together. So let's use an example. Let's use some prototypical light general aviation plane like a 172 that has a best glide speed of 65 knots, maximum gross weight of 2,400 pounds. Okay, well you're not flying at maximum gross weight today. You might only have one or two people on board and half tanks. So let's say you're at 1,800 pounds right now. You're going to divide that out, you get 0.75, take the square root, and that comes to 0.866. Multiply by 65, and you get 56.2. Now, would you agree that there's a difference between 65 and 56? So just that 9-knot difference there is the difference between flying an incorrect speed and a correct speed in an emergency situation. So the principle is the lighter you are, the lower this number is going to be. And so if you're flying by yourself with half tanks and you lose your engine, you're not going to automatically pitch for 65. You're going to pitch for a speed that may be between 5 and 10 knots slower than that. And so just that by itself is what you need to do to get the book performance out of the airplane. What happens if you fly at 65? Well, you're just trading useless altitude for nothing, really. You're wasting it. And so keep that in mind. That's the first principle that I want to talk to you about. And if you're flying a plane for some reason that has no best glide speed published, it's probably going to be very close to VY. So we've talked about best glide, and pretty much everybody understands that. But my point is that the only speed that you need to know? And the answer is no. There's another very critical speed that you need to know that unfortunately for some reason doesn't get taught most of the time. It's a concept that is very, very familiar to the glider community, but just for some reason it hasn't made it over to the power flying community. And that concept is minimum sink airspeed. Now, again, we said best glide was to get forward, right? It gets you the furthest forward of any speed. If you glide slower than best glide, you'll land short. If you glide faster than best glide, you'll land short. So it gets you the furthest forward. But that best glide speed is only good when you're trying to glide to something far away. What is minimum sink airspeed? It gets you the least altitude lost per unit of time. So rather than maximizing range, it's maximizing endurance or time in the air. And so would you agree that if you had a field directly below you and you lost your engine and you're at 5,000 feet, what's more important, gliding far or staying in the air? You're going to stay in the air so that you can try to rectify your engine failure or do what you need to do to circle around and land. And so it's a very important airspeed. Now, there's some mathematical ways to approximate minimum sink airspeed, but probably the easiest way to do it for you would be to just do it experimentally in your airplane. And what you're going to do is take your airplane up, put it in a power off descent, and I would start at whatever the max or the best glide speed is, and then slowly reduce the airspeed a few knots and see what kind of descent rate you get on the vertical speed indicator. And then you reduce the airspeed a few more knots and see what kind of descent rate you get, and reduce it a little more. And so as you do that, you're going to see a trend on your vertical speed indicator where at best glide speed you might be coming down at 500-600 feet a minute, and then it's going to eventually work its way to about 400 feet a minute, or whatever it may be in your particular airplane. And then as you keep slowing down, now it's going to start to increase the rate of descent again, because what are you doing there? Well, now the increased or the induced drag is starting to rise, and now you're getting closer to a stall. So it turns out, if you plot it, it's what we call a polar curve. And so if we were to plot, on the x-axis we're going to plot airspeed, and on the vertical or the y-axis we're going to plot rate of descent. And so it basically, if you did it and just connected the dots, it would look something like that. Okay, so this would be, 65 knots, your best glide speed here. And so your minimum sink airspeed might be 55 or something like that. And then as you see, as you go slower down towards 0, now you're getting closer to a stall and your rate of descent's going to increase. But there's a pretty substantial difference in sink rate between the two. It might be 100 or 200 feet a minute, right? And in an emergency, that might get you a couple extra minutes, 1 or 2 extra minutes to deal with the emergency. So this is a very important speed, minimum sink airspeed. And if you want to approximate, it's probably near Vx. So the upshot of this is we need to eliminate the rote level of understanding that we have about best glide speed. Best glide speed, first of all, is a dynamic speed. It changes with weight. And secondly, it's not the most important airspeed in an emergency. It's only the speed you're going to shoot for if you're trying to glide to something. And people have talked about this off and on. Barry Schiff did a column one time where he went up for a checkout with a fairly young flight instructor in a 172, and the flight instructor pulled an engine on him, and so Barry said, well, the field is directly below me, so rather than go to best glide speed, I'm going to go to minimum sink airspeed. And the flight instructor, oh, no, you have to use best glide speed. And that's what I think is the problem. There's just this rote level of understanding that keeps getting passed. But the idea is in an emergency, you need to be the master of the aircraft. And what does being the master of the aircraft mean? Being the master of the aircraft means that you do whatever you need to do to meet the needs of the emergency. And so blind adherence to one speed, if you don't really understand what that speed is, that's not a good thing. So we need to eliminate that. Now, talking about speed also, glide speed can and should be adjusted for wind. This is another concept that glider pilots are intimately familiar with. They teach it from day one. And the idea is if you're going into a headwind, you increase your glide speed into a headwind. And if you're gliding with a tailwind, you slightly decrease your glide speed to achieve better glide ratio. And so if you're gliding into a field, think about it. Let's say you're 2 miles from a field, and this is an unusual scenario, but let's say there's a 50-knot headwind on the surface, and you're gliding at 60 knots. Well, are you going to make the field? No, you're going to just come down like an elevator because you're going into a 50-knot headwind. Well, some people might say, well, why don't you just turn around and glide with the tailwind? Of course, that'd be preferable. But if the field is right there, and you have the altitude to do it, you can increase your glide speed to achieve better penetration into the headwind and make headway over the ground to get to the field. And so the rule of thumb that glider pilots use is to take whatever half of the steady wind is. So if you had a 10-knot wind, you'd add 5 knots. Add 5 knots to your glide speed to achieve better penetration into the wind. Now, if it's a tailwind, you're going to do the opposite. You're going to slightly reduce your glide speed, but not by as much, because you risk getting into that situation where you start getting in the area of reverse command and induced drag starts rising. So the idea is, people think, oh, I have to hold 65 knots every time, and that's the only speed I'm going to ever use in an engine failure. And the idea is minimum sink airspeed is just as important, and we're going to talk a lot more about energy shortly, and so minimum sink airspeed is incredibly important for energy. But the idea is you just can't hold one speed in an emergency. Now, how many folks fly an airplane that has a constant speed propeller? A couple people here. If you do that, to get the maximum glide range out of your airplane, you need to be sure to take the propeller lever and put it to the low RPM position. So in this instance, this would be set up correctly where the prop lever is pulled all the way back. And it's very noticeable. If you take your plane up and you go and you have the prop lever all the way forward and put it in a power off glide, that prop at the low pitch, high RPM stop is sucking an incredible amount of energy out of your glide. If you take that prop lever and pull it all the way back, as long as you have oil pressure, and most of the time you still will, because as we see, most engine failures caused by fuel problems, not by stuff blowing out of the engine. So if you just lost all your fuel or something, you still have a windmilling engine, you still have oil pressure to move the propeller, pull that prop lever all the way back, and it's almost like somebody's accelerating you, because the drag just disappears, because all that slipstream energy isn't being sucked into turning the propeller. And so let's talk about some characteristics of a good emergency landing site. Let's see, we want far away from the FAA, right? Any other suggestions for a good emergency landing site? Flat, okay. Flat. Let's see, we probably want four-star hotel nearby, right? I'm sorry?
Softest spot at the lowest speed.
Okay, I hear softest spot at the slowest speed, and the slowest speed part is exactly right. How about a place where there's a Walmart nearby so you could change your shorts after the emergency is over? But you see some pretty crazy emergency landing situations here. And the idea is, commonly when I ask questions, I hear flat a lot, but sometimes I hear big, And the idea of this is I want to try to disabuse everybody of the notion that an emergency landing field has to be this big, huge open field, because it really doesn't. Unless the terrain is exceptionally severe, chances are that there is a spot nearby that you can put that airplane into, as long as you understand the information that we're going to talk about here. Now, one technique you can use is you could sit in your airplane and draw an imaginary arc from your spinner to your wingtip on the left and the right. And when you do that, you're guaranteed to glide to anything within that spot in a no-wind situation. Because picture yourself being on top of a big cone or a pyramid or something. You know, if you draw that pyramid out in front of you, you're going to make everything in that arc. The problem that I have seen as a flight instructor when I used to flight instruct and many other instructors see is all the time when you simulate an engine failure for someone, you say, where are you going to land? And they look immediately out on the horizon. And they've picked probably the farthest away field that they can find. And the idea is, yeah, okay, your people's attention is out there because they're used to looking outside the airplane, out on the horizon. But you need to bring your attention in closer to the airplane and find something that's closer into the airplane, which is going to give you more time to deal with the emergency rather than trying to glide to some 10-mile away field, and maybe you're going to make it, but probably you won't, because typically most inexperienced pilots, they pick a field that they think is reachable, but it really isn't. And so that's one technique you can use. But another technique that I want to teach to you is the rule of thumb. And literally, this is a rule of thumb. Now, the typical GA airplane glides at about a ratio of 10 to 1. Some airplanes are less, some airplanes are more. Like a 150 glides at about 7 to 1. But if you take a 10 to 1 glide ratio, that's about a glide angle of 6 degrees, 6 degrees down. And so if you take your thumb and you hold it out at arm's length like this, the distance from the tip of your thumb to your big knuckle, that subtends an arc of 4 degrees at arm's length. And so if you do that, what you do is you take a thumb and a half below the horizon, and that everything beyond that point you're not going to make it, and everything closer in you will. So that's that technique to bring your focus back in towards the front of the airplane. So anything within that 1.5 thumb length is probably reachable in a no-wind situation. Now, knowing your airplane, we talked about best glide speed. You should know best glide speed in case you need it to maximize range. But the idea is you have to be the master of the airplane, and you need to fly the plane at whatever speed is necessary in order to deal with the emergency. So if you need to maximize endurance, go to minimum sink airspeed. If you need to glide into a wind, you could increase the speed slightly. But you should understand your airplane and understand the emergency procedures that are necessary in the airplane to deal with the emergency. Develop a flow check for an emergency. In a lot of single-engine Cessnas, you can do an L flow, which starts down at the fuel selector, goes up towards the mixture and carb heat, and then over to the ignition and the primer. So that's a quick flow that you can do. You can, if you have a more complicated airplane, think of the things that you're going to need to reach for to try to check in an emergency. Because, well, then going back to the complex airplane, this is a turbo aero, but you'll notice that there's all these associated conditions to get the maximum glide performance out of the airplane. Flaps up. 97 knots, again, is the published best glide speed for maximum gross weight. So if you're less than that, you're going to reduce this speed. Gears up, powers off, max gross weight, prop full decrease, which we talked about in zero wind. But the thing is, if you're sitting in your airplane and the engine starts acting up, what do most pilots start to do? What do most pilots start to do? Fiddle with stuff, right? Okay, well, going back a few slides, what did we say the most important thing to do was? Establish a glide. Okay, so before you do these troubleshooting procedures, you need to set the plane up in a glide and keep it there. And the problem that many general aviation pilots have is they have a hard time holding a precise airspeed when their attention is diverted among different things. So they start troubleshooting and the airspeed starts to change. So the idea is you have to get the airplane established, trim it so that it will hold that speed, and then start troubleshooting. So this is the troubleshooting procedure that's recommended in the old flight training handbook. But you can use the ABC technique. A is airspeed, B is pick out the best field, and then C, divert your attention inside the cockpit. Okay, now we're going to talk a little bit about stress here. Most forced landings, the fatalities, I believe strongly, are caused by a failure of the mind more than they're a failure of the airplane. Because pilots get into a panic situation and they forget the things that they need to do, and they give up control of the airplane. They just throw their hands up in the air and say, forget it. Or they freeze up, or they don't know what to do. And when the panic sets in, you're not a pilot anymore, you're a passenger. And the idea is I keep going back to this, you need to be the master of the airplane and you need to be in control of that airplane until it comes to a stop. Now, most people work under a small amount of stress. So your performance gets better with a small amount of stress. But as stress starts to increase, then of course your performance starts to fall. And comparing a simple or routine task to a complex task or emergency, your performance level starts to fall off quite a bit more. You know, if I gave you a very boring task like sitting in a room and there's a light bulb and a button, and anytime the light bulb comes on, you need to hit the button. Well, okay, that's an easy task, but if I ask you to do that for 12 hours, you're going to get bored, you're going to maybe fall asleep, and your performance will naturally start to suffer, right? So I introduce a small amount of stress. I call my friend Guido. Guido sits next to you with his newspaper, and anytime you fail to push the button after the light comes on, he gives you a whap. Okay, well that's going to make your performance good, right? Well, if Guido just starts whacking you, whether or not you're pushing the button, now your performance is going to start to suffer. And so you're task saturated. You're getting too distracted by, getting beat up to deal with what's going on with the light bulb. And so you get task saturated in an emergency a lot faster than you do in a normal or routine task. So you have to understand that that's going to happen. So how do you deal with being task saturated? Well, you shed the load. And the way to do that is to focus on aircraft control and then the other things that you need to do. So it's the old aviate, navigate, communicate. So how do we deal with stress? Well, you can read the caption on this cartoon here. And basically I characterize this as a poor response to stress. Whereas this one is probably a little bit better response to a stressful situation. He's not even really caring about the fact that the roof just ripped off. But the bottom line is I said aviate, navigate, communicate. Another way to look at it is I will maintain aircraft control, analyze the situation, take appropriate action, and land as soon as conditions permit. The bottom line is a successful emergency landing under adverse conditions is as much a matter of your mind as it is of your skill in flying the airplane. So we've had an engine failure and we've picked out a field and we're gliding to it. Notice I've underlined the word managing. This is a very critical concept as far as I'm concerned. You are not just an idle passenger on board this plane. You have to actively manage this approach as you go down. And so if you're looking at the diagram, you're going to retract the flaps and gear to minimum drag configuration and spiral over the field and then land into the wind as much as possible. But the idea is it's an active process. Managing is an active process. So you're not just going to set the glide speed and then throw your hands up and wait for the airplane to hit the ground. You're going to manage the thing. If it's not doing what you want to do, you've got to change something. Either adjust your speed, pick a different spot, do something. It's an active process you need to be in control of all the way to the ground. That's how you manage stress, is you take control and you manage the thing all the way down. And so you're going to be looking at how the wind is affecting your position over the ground, how much altitude you're losing with each turn, and then introduce drag at the appropriate time and then touch down. Now, with flight instruction, one technique that's used to train flight instructors is the idea of breaking tasks down into smaller tasks. And one way to look at this emergency landing situation is to look at it as if it was just a turns around a point and then a 180-degree power off approach. So you're just going to do turns around a point in that descending configuration, timing your descent so that you end up at that key position at about traffic pattern altitude or whatever altitude you want to make that power off descent, and then just do a 180-degree power off descent. Fly it like you would a normal power off traffic pattern approach. And then this comes from Kirshner. I'm not real fond of the fact that he says overshoot through the final and then come back, because we've seen that can be a risky scenario. But the idea is if you had a field and let's say the wind was coming from here, if you came like this and you were low, if you were too low, you would just turn directly into the wind and land. Well, if you were high, you might take it out a little further and then maybe come back sort of still into the wind, not directly into it, but you could still land into the wind, or even further, then turn and land. the idea is you've got to manage the approach, see what the wind is doing to you, and then adjust your speed and adjust your turn points so that you can land basically into the wind, but that you do it just like you were flying a traffic pattern at the same altitudes. So the bottom line is the speed is the thing. We've already talked about minimum sink airspeed versus best glide speed. And again, I hate math, so I'm not going to belabor this too much, but this is the formula for kinetic energy. The upshot of this is that doubling your ground speed quadruples the amount of energy that must be dissipated in a landing. And so what does this mean? The slower you come in, the less energy that has to be dissipated, the less ground roll distance you need. Conversely, reducing your ground speed in half reduces the destructive energy to only 1/4 of what it was. So how are you going to reduce your ground speed? Well, the first big way to do it is by landing into the wind. Okay, so that more than anything is going to have a profound effect on your ground speed at the time of touchdown. All that energy has to be dissipated somehow. So even a small change in your ground speed from the pilot technique or the wind is going to dramatically affect the outcome of a forced landing. An impact at 85 is twice as hazardous as one at 60. And conversely, and also similarly, an impact at 120 is 3 times as hazardous as it would be at 70. So the idea is you have to come in as slowly as you can. Now, GA aircraft are designed to protect you 9 Gs forward, and this is under the old CAR 3 regulations, 1.5 Gs sideways and 6 Gs in a downward direction. This means the seat attach points and your seat belt attach points are stressed to withstand a 9 G deceleration. Okay, so what this is guaranteeing is that the seat and the seat belts will contain you within the aircraft even if you decelerate at 9 Gs, and that's a very survivable deceleration. Now, with the fact that you can decelerate at 9 Gs, you don't need very much distance to stop that airplane and still be able to walk away. Now, I'm going to throw this out to the audience. What if you were touching down at 50 miles an hour? What kind of distance do you need to stop an airplane at 9 G deceleration? Anyone? Just throw out a number. What do you think you need to stop? 250 feet. Okay. You need 9.5 feet. How about at 100 miles an hour? Remember, it's not linear. It goes up by force, so it's actually a little more, but it's 37.6 feet. Still, does this mean you need a 5,000 foot long landing field to make a successful emergency landing? No. If you land in a field and you're able to decelerate the airplane by using the landing gear to shed the landing gear or something like that, or go through some crops or something that's going to decelerate the airplane, you're going to need very little distance and still be able to walk away from that situation. Now look at the graph here. This is a graph comparing best glide and minimum sink with the amount of energy. So you see that at best glide, of course, you're at a faster speed. The amount of energy that you need to dissipate is quite a bit more than you would at minimum sink airspeed. So at touchdown, what speed do you want to be at? Best glide or minimum sink? Minimum sink, exactly. So this is another reason why understanding minimum sink airspeed is critical for a good outcome in these situations. Now, touchdown during an emergency landing should be at the slowest controllable speed using all the available aerodynamic devices, flaps, landing gear, etc. Stalling it in is a bad idea. The airplane is built to land on its wheels, not on the roof. And so your survival, and again, the topic is surviving forced landings, your survival is determined by your speed and the angle of impact. Now, before you touch down, you're going to want to brace for impact, talk about what you're going to do with the doors of the airplane. Some manufacturers say pop the doors open, others say leave them shut. The FAA's the Small Aircraft Directorate recommends leaving them shut to preserve the integrity of the fuselage. But if your aircraft manufacturer says pop it, then you would follow whatever the manufacturer's recommended procedure would say. Of course, you're going to shut off all possible sources for post-crash fire, the electrical and fuel systems. And of course, brief your passengers and keep them in the loop, because after all, they may be the ones that have to shut switches off and open doors for you if you're incapacitated. So, well, actually, I gave away my secret there, but the question I ask is I say, which would you rather land in, beans or corn? Okay, yeah, I gave that away because you saw what happened in the, okay, so this is beans. All right, well this is corn. There's actually a story behind this. This was a guy that had an engine failure in this tri-pacer, or I guess this is a pacer, and he was about 6 miles away from the big airport, and he lost his engine due to fuel starvation directly over a private strip. And he lost it directly over a private strip, but he said, no, I think I can make it to the big airport. And the controller said, okay. So he came in and he made it this close to the runway. Here's the runway, and there's some mowed grass, and then you see he made it in about the last 10 rows of corn. So what happened was he got down too low, and he kept milking the stick back and back and back, and eventually he just stalled and mushed into the corn, and that's why the plane flipped over. But assuming he had still been at flying speed going into the corn, this is probably what would have happened. Now, I consider this to be a photograph of a textbook emergency landing. Why? Well, first of all, the airplane is upright, the crew compartment is intact, very little corn is pushed over, which it seems to indicate that he came in at a very slow airspeed, and so all he would have to do is unfasten his seatbelt and get out of the airplane. Easy as that. So if you follow these techniques, you can have a very, very survivable situation. People often get most concerned about landing in trees because it's such a frightening thought, but even this shows you that landing in trees can be a very survivable situation because, after all, again, the crew compartment is intact. The engines have separated from the aircraft, but non-essential pieces of the aircraft are very good to use in eliminating crash energy. And so as long as you preserve the integrity of the crew compartment, the chances are quite good that everyone will walk away. Here's the statistics to back this up. In '98, Journal of the American Medical Association published a study of crash landings of GA airplanes 10 seats or less from '83 through '92. And of course, they adjusted the data to eliminate variances in pilot age, flight hours, and so forth. What were the conclusions? 62% of forced landings result in no injuries. Only 5% have a pilot fatality. Well, what can you do to minimize your risk for a pilot fatality? Fire or explosion after landing. Well, what can we do to minimize that? Shut off the master switch, shut off the fuel. Failure to use lap belt or shoulder harness. Very important. That's what's going to allow you to stay retained in the airplane during the deceleration. Finally, situations where the aircraft is completely destroyed. Well, situation where the aircraft is completely destroyed, it probably came in at a very steep angle or very high velocity. The point is that all of these three things are directly controllable in one way or another by the pilot. Again, you can do all the things to minimize these three risks, and the chances are excellent that you will walk away with no injuries. Now, of course, file flight plans and stay in touch, because even if you're injured, you want somebody to come after you, and keep in mind that cell phone service is not available everywhere, so that can't just be your only backup. And you might consider keeping an emergency kit in the airplane to deal with adverse conditions. Now, quickly, I'm going to go through the subject of low altitude engine failures, because this is another situation where there's many fatalities every year, and it really seems to be no impact in reducing these. The bottom line is that few pilots understand the consequences of turning back to the runway at low altitude. This comes from an FAA publication called The Impossible Turn, and I recommend you take a look at it if you have time. But the idea is that at various bank angles, this is how much lateral distance you need in order to accomplish the turn. So if you do it at, this would be at, I think it's these numbers are reversed. This is actually 45, this is 30, and this is 10. But at 45-degree angle of bank, you can make that turn in about 560 feet. But here's the problem. Okay, you turned around. Now you're laterally displaced from the runway by about 500 feet. So not only do you have to make it back to the runway, you've got to go sidestep back over to it. The shallower your bank angle is, the further over you are. So that just increases the amount of distance you have to glide to get to the runway. But more importantly, now you're downwind, right? Because you took off into the wind, and didn't we just get through this whole discussion about why having a high ground speed is a bad thing when you're touching down? So instead, why not just stay pointed into the wind to keep your ground speed lower and use this technique? This involves an arc either side of the nose 60 degrees. That's 120 degrees. If you think about it, that's 1/3 of the total horizon, 360 degrees. In 120 degrees, if you turn 60 degrees one way or the other, chances are that you will find something where you can put the airplane down. Too many people get in this situation where they're so focused on saving the airplane, they don't think about saving themselves. And the problem is that too many times these accidents are fatal. And so you really have to be focused on saving yourself instead of saving the airplane. The airplane is replaceable. There was a study that was done that was specific to the subject of turnbacks at low altitude. And they put pilots in a simulator and they told them that something was going to happen, but they didn't tell them what. And they took off. It gave them an engine failure shortly after takeoff. And of the pilots that attempted to turn back to the runway, only 42% were successful. And the criteria for success were that the airplane was not stalled and that it was a descent rate of less than 2,000 feet per minute or something like that. So these ones that weren't successful, they were really coming down. They were in a spin probably. And so only 42% of these pilots were successful the first time around. Even after repeated practice, the success rate only went to 62%. This is after as many as 7 tries. They still couldn't get it right. Whereas 100% of the pilots that landed straight ahead were successful. 100% every time. So keep this in mind. And I talked about why are you going to turn the airplane around and try to land it with a higher ground speed and probably end up in a stall spin situation. So have a plan for engine failure on departure. Take a look at the airport environment, see what's ahead of you on departure. Chances are you could probably find something in that 120-degree arc. When the engine quits, it's too late to put a plan together. Fight that tendency to turn back after departure and familiarize yourself with safe landings at the airport. The bottom line is, turnbacks do not increase your chances of survival. Stalling the airplane nearly always kills you. So under periods of high stress, we do not rise to the occasion. We sink to the level of our proficiency. And so the important thing is training in all emergency situations cannot be emphasized strongly enough. What can you do starting today? Well, get together with your favorite CFI to talk about some of these skills. Fly the airplane at minimum sync airspeed. Too many pilots are not comfortable flying the airplane at slow speeds just above stall. But the idea is these are the speeds that you're going to need to be at if you're touching down in an emergency situation. So get comfortable with it. Get comfortable with how the airplane glides. Employ the techniques that we've discussed, and you should practice spiraling descents, medium and low altitude engine failures. Conclusions. Be prepared. Don't panic. Know your airplane. Know that there's not just one speed to use in an engine failure. Know your terrain. Manage the approach all the way down to the ground and touch down as slowly as possible. If you want more information, there's a number of good publications. The first is a book called How to Crash an Airplane and Survive at that website. Also the old flight training handbook and the FAA's Impossible Turn publication. And at this point, I've got a few minutes left, so I'd be happy to entertain any questions from the audience.
Please raise your hand if you have a question. I'll bring a microphone.
Yes, ma'am.
Eric, what about practicing if you lose engine, you think you're losing an engine, and yet you still have some power. You go to your best glide. Do you let it sink, or do you stay at do you try and stay level?
What I would do is if you have a partial power loss, what I would do is slow the airplane to best glide speed, because that's a maximum range speed. Okay. And at this point, what is your priority is to try to find a suitable airport or some hard surface to land on, right? So that best glide speed is going to get you the maximum amount of range for each foot of altitude that you're losing. So I would just slow the airplane to best glide. Depending on how much power you've lost, you may be able to maintain altitude at best glide speed. So I would just hold that speed and then try to get to an airport to land. Now, If the engine quits completely, then now your priorities have changed. Now you're not going to try to get somewhere, you're going to try to find a spot to land, and then I would go to minimum sink. Okay. In the back, please.
Yeah, when you are on downwind, say at 80 knots or so, well, 60 knots is up here. It's not down below. So just pull back and let it go up a little bit and get you a little more altitude.
Well, sure. Now, well, here's the problem with that, though. The conversion of airspeed to altitude is not 100% efficient. And so if you do a zoom climb to 60, what's going to happen? What are you going to have to do to hold 60 now? You're going to have to do a very large pitch change to maintain 60. So whatever you gained in altitude, you're not really getting a great deal for it. Yes, you got an increase in speed or altitude, but now you've got to make a very large pitch change and an energy change to redirect your flight path vector back towards the ground. And so what I would suggest, instead of doing like a zoom to lose those 20 knots, is you're going to gently increase the pitch attitude, let the airspeed bleed off, but maintain altitude or slightly climb, because then that way you're not going to have to really aggressively pitch it back over. Good question, thank you. In the front.
If you have a questionable landing area and nearby there is a water, either a lake or a river, which would you choose, and is there a reason for the difference? Well,
When you say questionable landing area, do you mean like trees or something that you're not comfortable landing in? Or, well, there's advantages and disadvantages. And if you came in at a slow speed and ditched, ditchings can be survivable at low speed, but it's something that you can't really practice, so the outcome is a little unclear. The other problem that I have with ditchings is frequently the airplane flips. And now you're most likely underwater in an unfamiliar environment, and you need to release your seatbelt and exit the airplane. And that's something you can't really practice for. You're just, you're in the situation. Whereas you saw that picture with landing in the trees even, you could land it in trees, and if you come in at a slow speed and land in the trees, and you get the airplane in a good position where the tail is down and the nose is up, and you're at a slow flying speed and you just fly it into the trees, I would say that the chances of survivable are greater in that situation than perhaps drowning in an inverted airplane with a ditching. So with that, I thank you so much for attending, and we really appreciate you coming, and have a great day. Thank you all.
And if you don't want to meet Eric, come up and see him anyway.
That's right. Come on up.